Hi, welcome to another edition of Calculus 2. Today we are going to talk about the very fascinating topic of numerical integration. Let's go ahead and see what this topic is all about. So, in Calculus 1, you are introduced to the topic of definite integral. Over there, it is described as the area on the graph of a function between two limit points. So if I have this function y equal to f of x and I have two numbers in mind, a and b, then the area under the graph of this function between a and b and over the x-axis is what is denoted by this definite integral notation, and then you learn how to calculate this. There, the main tool that you have is fundamental theorem of calculus. You calculate the antiderivative of f, plug values a and b in it, subtract, and that is what the area is going to be. Now in this semester we have learned various ways of actually calculating an integral. We have introduced you to a long list of substitutions and various type of techniques for calculating an integral. As it turns out, all the methods that we talk about are only applicable to a very tiny fraction of all the functions that are out there. As if there is an ocean of functions out there and we have picked a thimbleful of these functions and describe what to do with them. The question remains, how about all the rest of the functions that are in that ocean? What are you going to do with them? How are you going to integrate them? Numerical integration is a topic all by itself, which in one of its chapters tries to answer this question. How would you actually calculate a definite integral? All the students in mathematics, engineering, physics, and so on are going to have a course later on, perhaps an optional course on numerical approximation. Sometimes the course is referred to as numerical analysis. What we are going to do in this section is just take a look at some basic ideas there that relates to the chapter we are talking about. We learned about integration, so we are going to learn about numerical integration. So again, the idea is very simple. How do you calculate the area under the graph of a function? So the approximation we have in mind is, well, take this region that you want to calculate its area and cut it up to panels. So we are going to cut it up to panels, approximate the area of each panel by a rectangle, calculate the area of each rectangle and add them up. That would be an approximation for the area that you had in mind. So the idea is very simplistic and at the same time extremely powerful. Due to its simplicity, it's applicable to a huge array of functions out there. So instead of limiting yourself to that thimbleful of functions that you could deal with by all the substitution and tricks that you had, you can actually apply this to a very huge portion of the functions that are available. And what we are going to do is to just detail this and talk about how it's going to be carried out. It's very simple. It's essentially something you could have done in middle school, and at the same time it's very powerful. That's why it is so attractive. With a simple idea we can handle questions that arise in practice. So there are a large number of ways that this can be done. Let's see where the variety of approaches come in. First of all, we are going to take our region and slice it up in panels. Well, lots of choices there how you slice up a region into panels. to make it simple, we are going to make all of our panels to be same size. So it's a uniform cutting up of the region into these panels. In advanced practice, they do something more sophisticated than that, but right now this is sufficient for us to get started. Next, suppose I did cut up these this region into panels. Well, how am I going to approximate it with a rectangle? In Calculus 1, the Riemann's theorem that you learn over there is just pick any point on the function, use that as a height of your rectangle, and then you're all done. So essentially pick any point randomly and then you have a rectangle. But we want something perhaps a little bit more definite than that. We could have done random choice, but let's start with even something simpler than that. So in the left rule method, the idea that we have is that after you have sliced up your region, go ahead and pick on the left point of upper left corner of these panels. So here's a point, here's another point, here's a third point here. From each of them I draw a horizontal line, therefore I have a rectangle. Now I can go ahead and find the area of the first one. I've drawn it in yellow here, the second one is in blue, and the third one is yellow again. I calculate the area of these rectangles. I knew how to calculate the area of rectangles back when in middle school or elementary school. Just add them up and we are going to get an approximate answer. Now, question, why is this an approximate answer and not an exact answer? So let me ask you guys to think about this thing for a second and tell me, why is this an approximation? Sorry, I lost my page. Let's go back here and get my page back up. Well, it's very obvious why this is an approximation. This white area that you see here, you are not calculating that area. So in this picture we are underestimating the total area if we just add up these rectangles. So we might think about an alternate way. So instead of choosing the left point to make your rectangle, let's choose the right point. So when I slice up these this area into these panels, I pick on this point, and this point, and then I build my rectangle out of the height of the function at these points. And this is now referred to as the right rule, simply because this is at the right end of each of these panels. So in this case, we are overestimating. In this picture that you see, we are overestimating for obvious reason. We are going above the picture of the function, and therefore the area of the rectangle I'm calculating here is more than the actual area I want. Now in general, we don't know if you are overestimating or underestimating. If we know if you are increasing or decreasing, we can tell, but if you don't know that, it could go either way. So here are two methods. You can simply cut it up, make rectangles, add them up. All it takes is patience in carrying out a simple task. It's going to be a bit repetitive because you have to have lots of panels to have an good approximate answers. But the procedure itself is extremely simple. How about the rest of these things? After we do a few of the left and right rule, we start thinking about efficiency. Efficiency means how quickly are you going to come up with a good approximation. Well, what do you mean good approximation? Well, I want my answer here to be close to the actual thing. Here, the only thing that's left to you to improve your approximation is to increase the number of panels. As you increase the number of panels, the amount of area that you are underestimating or overestimating is going to decrease, and then you get a better approximation. The question is, do we have other alternatives, especially with the view toward efficiency, meaning with the fewest number of calculation I want to have a highest approximation I could. Well, there's a whole sequence of these things, and an entire course can be essentially dedicated to the topic. We're just going to go look at a few cases. We have so-called mid rule. Can you think about what is the idea of the mid rule? What do we do to calculate the approximate area with using the mid rule method? What do you think is the well, here's a picture. Does it give you an idea? Or the word mid rule, does it give you an idea? The question here, you're going all the way to the left. Over here you're going all the way to the right. It stands to reason, just stay in the middle. So whatever of these panels you have made, just go straight up in the middle of the panel, make a rectangle there, and then add up these areas. Now, can you think about why is this mid rule so superior to either of the left or right? It's a very simple, obvious reason. So here's our picture to remind us to think about this thing and try to answer it ourselves. So why is the mid rule superior to left or right? I'll pause this thing for a second and let me see. You can come up with the answer yourself. So it's rather obvious from the picture. When you draw this thing at the mid rule, on the half of this thing you're all underestimating, other half you're overestimating, so the two errors you're making have a good chance of almost canceling each other out. Okay, so here's obviously you're going to underestimate. Here you're obviously overestimating. Here on half the panel you're overestimating, the other half you're underestimating, and if you look closely you see that these two almost cancel each other out, and therefore mid rule is superior because its error is going to be less. Now it's significant to think about that the number of calculations that you are going to do is the same. The amount of effort you put into this is same as what you put in the left or right. In left, for example, I had to do 3 calculations. On the right, I had to do 3 calculations. Here I'm also doing 3 calculations. But if you practice this thing on any type of function, you immediately see how much better this thing is going to be compared to those. Are there other choices? We start to thinking about how to make these errors cancel each other out. One choice that comes to mind is so-called trapezoid rule. Let me ask you to think about this thing and come up with an explanation of what is trapezoid. What's the trapezoid rule? What do we do? Okay, so the picture is a little bit here small perhaps to show it, but what do you think our approach is going to be? Think about it for a minute and pause this thing and think about the process itself. So the idea is, after you cut this thing up into the panels, go ahead and connect the left point rule to the right point rule and thereby make a trapezoid. Calculate the area of this trapezoid. The yellow one, the blue one, and the yellow one, add them all up. That's going to be better than either left or right, simply because you're letting these two errors to almost cancel each other out. If you pay attention, you are going to see that there is a simple relationship between the result of the trapezoid rule and the result of left rule and right rule. What do you think I should do to left and right? So suppose I've calculated this thing, I've calculated that one. What's a simple way to calculate t? Again, pause this thing for a second and let me see that you can do it all by yourself. If you think about this thing for a minute, you'll see that the trapezoid rule actually gives you the average of left and right. Is that right? When you want to calculate the area of a trapezoid, you say upper base plus the lower base added up divided by 2 multiplied by the height. Well, This is going to be our upper base, this is going to be the lower base, and you're adding them up to calculate the area of the first one. For that reason, this turns out to be average of these two. Again, the amount of effort you put in trapezoid rules almost same as the left or right rule. Slight difference, but in practice that's not noticeable. Slight additional calculation you are going to do here, but in a typical application that is not a significant thing. So trapezoid, essentially same cost as either left or right, but due to the fact that we are letting the errors cancel each other out, we do a lot better here. So that opens the door to, well, can we improve that one and can we improve that one and so on. So in fact there is an entire sequence of these things referred to as Newton-Cotes rules. Newton is same Isaac Newton you hear everywhere else. And typically the engineers go as far as Simpson rule, and that is as good as anything for a typical application. For if you want to have a few decimal places of accuracy, this is more than sufficient. It turns out for the Simpson rule it's going to be rather hard to actually draw the picture, but explaining what we do in practice is going to be easier. Notice in the left and right we are approximating the function by just flat lines. So you're essentially making a stair step and then you say calculate area under that. That's for the left. Same way for the right. Mid rule is also a stair step, but the steps are chosen in much more intelligent way than these two. Trapezoid, you are approximating your function by a polygon and you are calculating the area under that. So idea of Simpson is that, well, go one level higher up. Instead of approximating with a straight line, go and approximate it with a parabola. So in each of these panels, what we do in the Simpson rule is to approximate the function by a parabola. Calculating area under a parabola is going to be quite easy, and we just add up all the pieces. This is going to take a bit more effort than the other ones, but it is amazingly efficient. And one way of describing what the Simpson rule is going to be, we're not going to prove this thing today, but just to indicate, this also relates to these two. Same way that trapezoid is the average of these two, S is also some sort of an average of M and T, but it's not a straightforward average, it's a little bit different. So I'm going to leave that as a big challenge for students who are interested in mathematics. What kind of average of M and T is going to give us the best of all words? And it turns out that you have to take twice M and 1 T and average them by adding these two and dividing by 3. So Simpson rule, one way to describe it is that formulation. Now in your text you are going to see a statement about the errors of each of these methods. The issue becomes more and more extensive. We are not going to talk about that. We are just going to talk about some basic examples of how do you use these things. So in my example, I'm going to go ahead, pick a function that's not overly complicated, so we don't have a distraction for the function itself. So I'm going to pick a function like x squared, which of course you know back in calculus 1 how to approximate the area under it. You typically want to use these methods for functions you couldn't do in calculus 1 or 2, but just to get started without having additional complication, we are going to take this example. So suppose we say find integral from 1 to 3 of x squared dx using left rule with 10 panels. Okay, we are going to refer to each of these things as a panel. or 10 rectangles or 10 intervals if you wish. Okay, so 1 is sitting for A, 3 is sitting for B, x squared is sitting for f of x, and we want to apply this method to calculate this. Of course, back in calculus 1 you had an easy way of doing this, and you say, well, find the antiderivative of this thing, which would be x cubed over 3. Apply the fundamental theorem 1 to 3. So you plug 3 in this thing, becomes 3 cubed, and plug 1 in it, becomes 1 cubed divided by 3, 26 over 3rd. All done. Why do you want to bother with something else if you have an excellent method? Well, if I had this thing e to the x divided by, say, exponential of x plus sine of x plus 5, or some mix of rather incongruous functions, I could not calculate my antiderivative. No amount of techniques we have learned in this course, or you learn in any other course, going to give you an antiderivative, simply because that function is too rare of a function, somewhere in the corner of that ocean of all functions there. Nobody ever bothered to investigate it, find the antiderivative for it, and essentially you're the first one to look at it. If you're the first one to look at the function, it's very unlikely you will be actually able to find its antiderivative, simply because nobody bothered to tabulate it. So none of this is going to be applicable. You have to have plan B, and plan B is numerical integration, which says I'm not going to be looking for these type of formulas anymore. I'm just putting that aside altogether. Go to a method that's going to be robust, is not going to require any of these algebra tricks or trigonometric substitutions or anything of that sort. I want to make it almost like elementary school. What do I do? So first of all, 1 to 3, 1 to 3. So I draw a real number line, hopefully with less wobble than what I drew it here. And so supposedly say 1 is here, and say 3 is here. Well, I want to make 10 panels. So how wide is each panel? I say from 1 to 3 is 2 units. I divide it by 10. That's going to be 0.2. So that means every step I make is going to be 0.2. So I go to say 1.2, and then I go to 1.4, and then 1.6, and so on, all the way. I go to, at the end, I'm going to have, say, 2.8. The last point is going to be 3. This 0.2, which was obtained from b minus a divided by the number of panels that is given to me, typically shown by n, has lots of nicknames. One nickname for it is h, another nickname for it is delta x, and some other nicknames out there in use also. So the first thing to do is to find your h or delta x. If you have 10 panels, how wide is each panel? Simply b minus a divided by number of panels you want. Notice a minor thing, that the number of panels is always one less than number of points that you have. Like here you have point number 1, 2, 3, 4. So you have 4 points and 3 panels. The discrepancy between these two typically throws off the students and programmers. How come one is more than the other one? But for obvious reason, because you're including both endpoints. Okay, so I can think about this thing as my starting point. This is my point A. The next one would be thought about as a plus h. Next one would be thought about as a plus 2h. Is that right? So h is sometimes called the run, or so you have different words used for it too. Run, step size. Other words is used, increment. All sorts of words used to indicate what we are doing here. So you're starting from left. Add the increment. Add the increment again. So it's as if you started at left and added double the increment, and then add 3 times the increment, and so on. The very last point would be a plus n times the increment. N times the h is going to be b minus a. If you add it to a, of course you get b. And it's good to remember the point right before that is a plus. Let me ask you, what's the last point? A plus what? Okay, think about this thing. What should I write here? A plus? Well, of course, it's going to be one less step than this one. Is that right? So one less step than that one. Let's remember it, that is n minus 1h. So in general, the sequence of points that you have can be written like this. Like if you want a formula for it, you can write it like that. But in practice, you have definite specific numbers. Like I went from 1 to 3 in steps of 0.2, so I have all these decimal numbers going to that point. Then what? Well, let's just draw a quick picture. So I'm not going to draw this thing to scale, just so that my picture fits here. So you have some function. So this is our function y equal to f of x. In this case, we have the simple function x squared. Well, how high is this function? I need the height because I need the height of the parabola. At the 1, my height is 1 squared. Let me exaggerate the distance, 1.2. At 1.2, my height is 1.2 squared. At 1.4, my height is 1.4 squared. So whatever numbers I have here, I have to plug it in my function, figure out what the heights are going to be for each of these rectangles. Then what? Well, keep in mind that you're making these rectangles and adding their areas. So what is the area of the very first rectangle? Do you remember what was the area of a rectangle? So obviously base times height. So area of the first rectangle, base is 0.2, height is 1 squared. Next rectangle, base is the same thing, but the height is 1.2 squared. Next rectangle is 0.2 times 1.4 squared. Down the road I go. I include all of these things. Crucial issue. What would be the last rectangle I'll be writing in this sequence? 0.2 times what? This is a very crucial point to make sure you actually understood what's going on. So do make an effort to think about. I am adding all these rectangles starting at 1, obviously. What is my last rectangle? What's the last height? So pause this thing and think about it, even if it takes 5 minutes, 10 minutes. Actually, once you pay attention to it, it's just 1 second. There's no calculation or anything to do. It comes to you right away. So pause it and do spend that 5 minutes so that you actually understand the topic. So notice in this picture, the last rectangle that you're adding is the one before the final point. So if you have point B, you have to go to the point right before that. So instead of a plus nh, you have to go to a plus n minus 1h, or point 2.8. 2.8 is the last rectangle you're building. So here, this is, so what happened here, this was the area of the first, this was the area of the second, and so on. So we go all the way to the very last. So the last one is from 2.8 to 3, but I'm building it on the left side. So the height of this is determined from the left, so it's 2.8. Okay, you notice that we don't have any algebra, trigonometry, or any of these things here, but you have to be carefully adding up the pieces. You cannot allow any of these things to escape from your attention. So that's a trade-off. No algebra or trigonometry, or actually not even calculus, but you have to be good with just very simple arithmetic. So we want to add all of these things. It makes sense to factor 0.2, and then I have 1 squared 1.2 squared, 1.4 squared, and so on down the road. I go all the way to 2.8 squared. So this is the approximate area. What is the exact one? In this case, we are lucky to have the exact answer, 26/3. What you do in many of these exercises is that you actually calculate this thing. So you have to patiently add these things on your calculator and find out what this thing is. So you have to find this, and typically your homework asks, well, write down this answer to 2 decimal places or 3 decimal places or something, and then perhaps compare against the exact answer, perhaps find out what the error is. So if you want to find the error will be, of course, the difference between the approximate answer and the exact answer. So typically error is defined either with the absolute value or just without the absolute value of the exact quantity minus the approximate quantity. So you find this thing and you find the difference, and that would be the error in the calculations that you have. So you need a basic calculator to do this, and then typically the n that you are dealing with your problem is some number between 5 and 10, so it's quite manageable to write all of these things and perform the operation and then find out what the approximate area is. Now while we are here, I'm going to leave that finding that number to you. Make sure you can find it on your calculator and just patiently calculate. What do you think is going to be the right rule applied to the same problem? What do we do with the right rule? So this one is going to be our left rule answer. My question is, well, the right rule is pretty similar to this thing. What would be the answer? Meaning, tell me what are the elements of the sum. Of course, I'm not expecting you to divine what the sum is. You have to use your calculator to find that, but the essential thing is to write that sum. You'll be asked to actually write this thing out in your handwritten solution. This has to be there, and then you approximate it with your calculator. Hopefully you get it right. The question now I have, again, you want to pause this thing and write a similar answer for the right rule. What is that going to be? So let's go to the picture to make sure. So what's the difference between right and left? At the right rule, the height of the very first rectangle is decided at the end of the rectangle, not at the beginning. At the end of the panel, not at the beginning of the panel. So in my problem, the very first height is 1.2. So that's a one difference. And how about the very last one? Well, the very last one is the last point of interval, which is b. So in my problem, I'm going to end up at 3. So that is so in this case, I'm going to write 0.2. The base is the same for all of these problems. So what did we say we write first? What did we write? 1.2 squared. That's the first height. 1.4 squared, and so on. What's the last item we write? Last item is the right end point, so it's going to be 3 squared. So that one starts with A, misses B. That one, the right rule, ends with a B but misses A. How about mid rule? What do you think is the mid rule? Well, again, in the mid rule, we are missing both the left and right. All the rectangles are decided at the middle of these intervals. So if this was 1 and this would be 1.2, what would be the middle of those two? What's the middle of those two? Well, obviously the middle of 1 and 1.2 is 1.1. The middle of 1.2 and 1.4 is 1.3. So for mid rule, we have 0.2. The very first one is 1.1 square, and we said what? The next middle point is what? 1.3 squared. What's the next one? 1.5 squared. Down the road we go. Let me pause this thing for a moment and push you to actually tell me what's the last height we are going to write here. What is the last height? The last height is going to be, of course, 2.9 squared. Now, I encourage you find these three answers and check to see which one of them is closer to the exact answer. You are going to find out the midpoint is a lot closer than either of these two. These two are considered to be very rough approximation. Mid rule is the intelligent thing to do. It's a lot closer to actual answer and with the same amount of effort. We said again, the reason this is much better than those two is that this obviously underestimates, that one obviously overestimates in this picture, and this one allows these two to cancel each other out. How about trapezoid rule? Trapezoid rule, you can sit down and calculate the areas of each trapezoid individually and add them up, or if you have already done these two, you can easily go ahead and make the trapezoid rule will be left plus right. You average them by this method, and then you have your answer all made. Of course, you can write it from scratch, but again, this being the introductory lecture on this, I'm not going to go into too much detail. Simpson rule, we said, is the most sophisticated of these things. Its cost is a little bit more than the ones that we have so far, but it has amazing accuracy to it. In fact, for the problem that we are looking at, it's going to produce the exact answer. It's very friendly to parabolas and such, but in general it does a very great job. And all that we have to do is, after we calculated this, we double that answer, and after we have calculated this thing, we take this and add them up and divide by 3. Why this very peculiar way of averaging? Well, it needs a couple of additional lectures, and hopefully we can encourage you to take our numerical analysis class or take it in your own discipline, and there's going to be a lot more to be said about this and the errors of them and such. I'll let you read about that and keep this lecture short so that we can go after a huge number of other topics we have coming up. Okay, I guess I stop here, and we are going to start a new chapter in the next lecture. Until then, good luck and God bless.